It's Mr. Kabbalah. This is going to be unit number 9, section number 3 on doing hypothesis testing with different distributions like proportion distribution and the difference of means distribution. I'm mainly going to be using Google Sheets. You can use your calculator, just be aware that sometimes you get different values on your calculator than you do on Google Sheets. Might be due to rounding or things like that. So if you have any questions, let me know and enjoy. All right, so this is how you do the calculations on Google Sheets. This is the eye surgery problem. The bolded ones here on the Google Sheet are values given to us in the problem. So I'm going to go through these pretty quickly. If you need to, you can slow down or pause the video. So they give us a probability of success of 30%, so that's 0.3. So the probability of failure is 1 minus that, so equals 1 minus this. It gives us these. We're going to need to calculate these in order to answer a question. So I'm going to do equals number of trials times probability of success, and number of trials times probability of failure. Now p hat is our sample proportion, so that's going to be this 88 divided by 225. The standard deviation, I'm going to show you the formula when we actually go over the problem. You can go back, I forgot what section it was or unit it was, but it's the square root, so equals square root of success times failure divided by number of trials, all in parentheses, like that. You should get this value. All right, p-value, we're going to do a z-test. So z-test, we're going to compare the p-hat versus the population, and the standard deviation is this one right here. So there is our p-value. Margin of error would be equals confidence. Okay, and then our alpha, which kind of is weird because our level of significance is alpha, but here alpha is the confidence level, or I'm sorry, 1 minus the confidence level, so 0.05 if we want a 95% confidence level. Standard deviation, and make sure you're clicking the right thing, and population size, 225. All right, now the confidence interval would be the p hat, so equals the p hat plus that margin of error, and then p hat minus that margin of error. All right, so in the on the Google Sheet, you saw that I used a standard deviation of the square root of probability of success times the probability of failure divided by the number of trials, and that's this right here. That's what I used. We learned that a little while back when we started to talk about the the proportion distribution, the p distribution. So we did all those calculations, and now we got to put it into context. So you can read this whole thing. I'm going to save a little time by not doing that, but we have to state the null hypothesis. So the null hypothesis would be that the proportion is equal to 30%. And what we want to test, these guys have a new, or these doctors have a new way of doing things, and they want to see, is that proportion greater than 0.3? So is it appropriate to use the normal distribution as an approximation? That's why we did these two calculations here. If these are both greater than 5, then yes, we can. So NP and NQ are greater than 5, so we can use this to approximate, or we can use a normal distribution to approximate this distribution. Going on, again, there's the screenshot of the data that we calculated. Should we reject or fail to reject the null hypothesis? How do you know? So this is where I'm going to use the p-value right here, and we're going to compare it to the level of significance right here. So 0.0014. So 0.0014 is less than 0.01, so we reject the null hypothesis. So this means that the data is strong enough to suggest that the proportion is greater with the new surgery. So if we construct a 95% confidence interval, I'm going to be using these right here. Okay, so we are being told that it's between anything 0.387 to 0.395. So what does that mean in context? That we can be 95% confident that the true proportion for is between let's say 39 to 40%. I'm rounding 0.387 and 0.395 using the new surgery, the new procedure. And does this support your decision to reject or fail? So we rejected it. So yes, because the stated 30% is outside of that interval. So the two calculations kind of jive with each other. All right, here's a seed germination problem. I'm going to go just a little faster. You can always pause if need be. It's going to be trials times success. This will be trials times failure. Success divided by number of trials equals square root of this times this divided by this. Where'd it go? 0.78 compared to 0.8 using the standard deviation. All right, now what I want to do here is the Google Sheet only calculates a p-value from a value to the right. This particular one wanted to know if it was changing, so different than 80%. So this value right here is actually from a specific value to the right. We want to get rid of that. We want the opposite of that. Now here's the thing, but not only do we want to the left, so this value right here would be to the left, but we want to the left and to the right because it's not equal. It's a two-tail, and this is the way we'd have to do a two-tail test on Google Sheets. So again, we have to the right here, to the left here, and so if we want both to the left and then an equal amount to the right, and I'm going to show you a quick visual of that in a moment, we're going to multiply that times 2. This is the value we'll use to compare against the level of significance. In any case, I'm going to keep going. There's our margin of error, so we're going to take our p hat plus that, or p hat minus that. So this is the seed germination problem. I already wrote out the null hypothesis and alternative hypothesis. So is it appropriate to use a normal distribution? This is where we use the n times p and the n times q. These both have to be greater than 5, and they are. So it is appropriate to use a normal distribution for this problem. So should we fail to reject or reject the null hypothesis, and how do you know? So we are going to look at our p-value. Now, I noted in the problem that we're going to use this one. Here's why. The value of 0.84 is talking about a specific value to the right. So all of this in red that you see is what the calculator gave us. Right now, we don't actually want that. We want to the left of that value, and then to the right of that value that is on the other side of the mean. So here's what I mean. We're not interested in the 0.84. We're interested in this 0.16 down here. So that's this value here. I rounded it just a little. So there's that 0.16. But we don't want it just to the left. We want that value, that same value down here to the right. Now I could flip it around and make it fit better. And so that's where this 0.317, nearly 0.32 comes in. We're combining this and this to do a two-tailed z-test. If you do this on a calculator, I believe it actually just does it for you. That's one benefit of the calculator. Here you'd have to know what type of test you're doing. So in any case, 0.32 is bigger than 0.05, so we fail to reject the null hypothesis. What does this mean in context? It means that the data is not strong enough to suggest that the proportion, and you could write this down, of germinated versus all is not 0.80 or 80%. So not strong enough to suggest that it is not 80%. Now it says to construct a 95% confidence interval. And so we found, and that's down here, anywhere between 78% to 80%. All right, and does this jive with our either we rejected, or I'm sorry, we failed to reject? Does that jive with failed to reject? So our null hypothesis is that the proportion is 80%, and you can kind of see in our confidence interval, we're 95% confident that that proportion is somewhere in that range, 78 to 80, and our probability of success is 80%. So it kind of goes, it does make sense in this context. So testing a paired difference, many statistical applications use paired data to draw conclusions about the difference between two population means. Data pairs occur naturally in, you see this a lot, before and after situations. So before treatment, after treatment. And this is why I italicize this. The same object or subject has to be measured in both of those situations, both the before and after, the same thing. We call these types of situations dependent samples. Dependent. So this is the heart surgery paired difference problem. Here are the 9 patients, so we need to finish this table. First, we're going to get the difference before counseling, after counseling, so equals this minus this. We can get it once, and then click and drag the blue box and get it for all of them. Now the population mean is 0. I put it here. I'll show you what I'm going to do with that in just a moment. And that's basically saying that our hypothesis, our null hypothesis, is that there's no change, that one minus the other is 0, so that they're equal. So sample mean equals average, and we're again going to concentrate on these differences. Sample size is 9. Sample standard deviation, so of the S of the differences. All right, now to get the p-value, we're going to be using a t-test because we don't know the population standard deviation. And on Google Sheets, if you want to do a t-test, you got to have a matched pair of data. So we're going to compare this A minus B difference column with the population mean column. You have to have a 0 in every single one. So you're going to type in t-test. Range 1 would be these differences. Range 2 would be all of the zeros. The number of tails. Now we were, I believe, testing to see, I think we're just if they were greater than. I might be misspeaking, but it's just we're going to do a one-tailed test and a 1. So there's our p-value. And then if we wanted to do a confidence interval, we would do confidence dot t 0.05, standard deviation, click on the right thing, and size 9. So that our confidence interval would be this plus the margin of error and this sample mean minus the margin of error. So, sorry, here's a screenshot of the Google Sheet. From the data, can we conclude that the counseling sessions reduce anxiety significance level of 0.01? So let's take a look at our p-value right here, 0.0012. 0.0012 is less than or equal to the p-value the alpha 0.01. So we reject the null hypothesis, which means that now the null hypothesis was that they were the same, so that basically the difference would be 0. So what we're doing is saying, no, it's not 0. We can say with 95% confidence that the difference between one and the other is between 15.7 and 50, let's say 51 point difference, or points, because I already said difference. Basically, this is saying that we can be 95% confident that their score before counseling was 15 to 51 points higher than after counseling. And if you read the problem, it did say a higher score meant higher anxiety. So this does indicate that the counseling sessions reduce anxiety. All right, this is the educational versus non-educational toys. So we're going to find the difference, educational minus non-educational. There's our population mean, so the sample mean would be the average of those differences. Sample size is 6 sets of twins. Now, before we do the p-value, we have to have zeros line up with, we basically need two ranges of the same size. T-test. Range 1, differences, range 2, this tail, 1 and 1, 1, that's how you do that. So the educational versus non-educational toys, the first question is, why are these considered to be dependent samples? It's because the same subjects are tested before and after the experiment. That's why they're dependent. Same thing, tested twice. So at the 5% significance level, data indicate the educational difference in the age at which a child learns to read. Now, to answer this, we need to take a look at the p-value. Now, you'll notice that this is slightly different than what I have in the Google Sheets video. In that video, I forgot to multiply times 2 because we were basically just saying, does it make a difference? So we're dealing with, the Google Sheet gave us a value here and up. We needed to double it to get the other tail as well. And even with that, the 0.046, let's say, is slightly less than our significance level, which is 0.05. So we reject the null hypothesis. And the null hypothesis would be that the average difference is 0, that there is no change between the two. If we take a look at what we notice, you can kind of get what this means. The confidence intervals down here. So the difference, we can be 95% confident that the difference between educational and non-educational will be between negative, let's say 0.1 and negative 4.6. Now, in terms of what this means, you're dealing with two kids. One has educational toys, one does not. They're twins, so I guess theoretically there's no difference between them genetically. In any case, these numbers here in the confidence interval suggest that these were in months it took to get to reading level, a certain reading level. So these indicate that those with educational toys, at the very least, are going to be ready about the same time as those with non-educational toys, or at the very best, almost 4 to 5 months faster, so negative, because this, the educational minus non-educational, to be negative, this one would have to be smaller than this one. And that's how we'd get a negative value. So we're 95% sure that the educational toys do make an impact. So there you go. All right, so to kind of show you the difference between dependent and independent samples, think of this. A shoe manufacturer wants to determine if the average length of a person's left foot is slightly longer than the average length of a person's right foot. If they select 60 random people and measure their left foot and the right foot, would this be considered independent or dependent random sample, and why? This would be dependent because the same person is tested. Okay, whereas if they select 60 random people and measure their left foot and then select another 60 random people and measure their right foot, would this be considered an independent or dependent random sample? This would be independent, different people for each one. Okay, the size of one person's left foot has no effect on the size of another person's right foot, whereas if it's the same person, generally, the size of your left foot does affect, or is related to the size of your right foot in general. Okay, so that's the difference there. You're going to see me on the Google Sheet use, oh, I'm sorry, there's a few more notes. We were just doing dependent between the paired differences. Okay, in the next set of problems, we're going to be doing independent, so not the same population being tested. Independent. Sheet, so just want to know where they came from. All right, so this is the camp stoves problem. We've got the data right here. Population mean is 0 because we're going to be testing the difference. So the hypothesis would be that they're the same, or that the difference would be 0. Same thing minus same thing equals 0. All right, the difference of the means, we've got equals 11.4 minus 9.9. Now, the standard deviation of the differences, I just showed the equations. Now, it's not too bad. It's the square root of, and then in parentheses, you're going to have to do another set of parentheses. It's the standard deviation and then squared. So I'm going to hit caret squared. And then it's divided by the sample size of the first model. Then end those parentheses, and then we're going to add standard deviation of the second model squared divided by its sample size. Okay, now we'd have to close up another set of parentheses. You can kind of see what Google Sheets does. It keeps track of those parentheses for you. And then you should get that as your standard deviation. Now the p-value, we're going to do a not a t-test, we're going to do a z-test, z-test. And we are going to compare this difference to 0 using this standard deviation. Now, in the problem, it was talking about camp stoves, and it was asking about, is one different than the other? So again, this p-value here is a value to the right. If we want different, we need to the right, and then that equal amount on the other side to the left. So I'm going to do equals 2 times this. And this is what I'll use to compare against the level of significance. So the camp stove problem, we want to know at the 5% significance level, does the data suggest that there is any difference between the two models? So we're going to take a look at this p-value. Remember, that's the one that was doubled because the Google Sheet only tells us from a certain value to the right. So we have to know how to adjust it to tell us what we want. In any case, since the 0.20 is greater than 0.05, we fail to reject the null hypothesis. Okay, so basically this is saying that, within reason, the data is strong enough to say that perhaps there is no difference between those two camp stoves. All right, so here we have two brands of headache medicines. This is going to be the difference of means. So again, the population mean is going to be 0. Difference of the means, so equals this minus this. Standard deviation of the differences. I showed the computation, or the equations earlier. We got to do the square root with parentheses, and then each of these divisions, so it's something squared divided by the number of trials. So, and there's 2 of them, so we have to do each of those in parentheses. So it's this, sorry, I got distracted. It's the standard deviation squared divided by the sample size of brand A, close those parentheses, and then add to it parentheses squared divided by that sample size. Now be careful, if you don't close all of your parentheses right, it's going to give you an error, so make sure you do that right. All right, p-value is going to be, in this case, we know the standard deviation, so it's a z-test, and we are going to compare our difference to 0 using our standard deviation, and that's going to give us that value. Now again, that's from a value to the right. This is asking basically check to see if there is a difference. So either more than or less than, so we need to double this p-value. Okay, so we're going to compare that to the level of significance to make our decision. So with the headache medicine, brand A, brand B, we did our calculations in that Google Sheet. Perform a test to see if there is a difference between the 2 brands at a 5% significance level. So again, we're using this p-value here for the two-tailed test. So 0.38 is greater than 0.05. So we fail to reject the null hypothesis. And with these, the null hypothesis would be that the difference is 0, that they're both the same. So in this case, yeah, we would fail to reject the null hypothesis, which means we would kind of say, well, yeah, they're pretty much the same, at least until we do more testing. A couple of things before we get to our last test. We're going to be testing the difference of proportions. When comparing populations using difference of proportions, statisticians are usually testing a null hypothesis that they're both the same, or that the difference is 0. In these cases, the population proportions are unknown, so we have to use what is called a pooled estimate. So kind of like everyone in the same pool. So pooled estimate of proportion denoted by P with a straight bar above it, P bar, kind of like X bar is the sample mean. This is kind of a, in a way, related P bar. Essentially, it is the total number of successful trials divided by the total number of trials. This gives the best estimate under the assumption that P1 equals P2. A couple calculations that you will see. The standard deviation of difference of proportions, probability of success P, probability of failure Q for each sample, for each population or sample, I guess either one, and then N1, N2 are the number of trials. You might also see there's P bar, it's the total number of successes divided by the total number of trials. Q bar would be 1 minus that. The standard deviation of pooled estimate of proportion is taking those and multiplying them together and dividing by the sample size of each sample or population sample that you're talking about. So that's what you're going to see in the Google Sheet coming up about pooled estimates and proportions. All right, so for this voter registration problem, we're going to do probability of success for each group. So that would be success divided by trials. And then this would be the failure would be 1 minus that. All right, for group 2, the ones that were sent reminders, Just kind of a note, some people say, well, clearly this, second group was higher than the first. Why can't we just use that? Well, you kind of can in some respects, but if you really want to get detailed and really get into the nitty gritty, you've performed these tests to kind of say, maybe it was just a fluke chance that group 2 had maybe some members that are going to register no matter what, and maybe they didn't need reminders. And anyway, so there's a bunch of variables, and kind of doing these tests gets to the bare bones of it to really make a decision whether it truly is higher or if it was a fluke. All right, in any case, difference of proportions, we're going to do this minus this. Pooled estimate for success. So that's going to be our new thing here. We're going to take the successful trials. Now notice I'm going to do parentheses because I'm going to want this equation to add first. So these added together, divided by, again, parentheses, and then trials added together. So again, notice how I had to type that in. If you don't type it in right, you're not going to get the right thing. All right, pooled estimate for failure would be 1 minus that. All right, the standard deviation, I showed you the equation just a moment ago. It's the square root of, and again, note the parentheses. I'm doing P bar times Q bar divided by, let's N1. And then plus parentheses. These two again times and divided by, now it happens to be the same number here. That's not always going to be the case. So there's our standard deviation. So we can get our p-value. So the z-test. We're going to compare the difference to 0. Okay, because with differences, we're testing to see if they're the same or if that one minus the other is 0. That's kind of saying the same thing. Standard deviation. And we get this this p-value. Now that's an extremely large p-value, but remember that Google Sheets goes to the right. And this is actually asking, is the first group, did they do this less than the second group? So we actually want to go to the left. So that's why I put a little box here. Okay, we actually need to do 1 minus that p-value to go to the left. So again, this value here is to the right. This value would be to the left. And we'll use that to check our level of significance. So using a 5% level of significance, what can we conclude about the clerk's claim? The clerk was saying that we should fund this program because the data show that when the reminders are sent, they're more likely to register to vote. So let's take a look. Again, from the Google Sheet, there's our p-value. And since 0.0009 is way less than 0.05, we reject the null hypothesis. And with these situations, the null hypothesis is that they're the same or that the difference would be 0. So we reject that and we go with our alternate hypothesis, was that in that they the first group that didn't get sent reminders is actually registered to vote less than the group that did get reminders. And we are pretty sure, well, I guess we don't know for sure because we didn't do a confidence interval, but we can reject the fact that they're the same. All right, now this one's going to sound weird because I'm going to call probability of success that somebody chosen at random is dropping out of school. So that's going to be a little weird moving forward, but that's what we got. So probability of success, 12 out of 153 in Oahu. So probability of failure would mean that they stay in school. Genesee County equals 7 out of 128. All right, difference of proportions. So equals this minus this. Pooled estimate for success. So again, watch your placement of parentheses. We're taking the successful, or the people who dropped out, and we're going to divide by the sum of everyone we contacted. All right. Pooled estimate for failure would be 1 minus that. Standard deviation is the square root of these two things here multiplied together and then divided by the number of trials. So notice the parentheses, I'm going to do pooled success times pooled failure divided by 153 plus other set of parentheses, same two things, times pooled failure divided by this time 128. And those parentheses and the square root parentheses, and then get our calculation. So our p-value would be a z-test comparing the difference compared to 0 using the standard deviation right here, and we get our p-value. And we'll use that to compare to the level of significance. So this last one about not voter registration, these are high school dropouts. We did our p-value test down here. Now, I don't think on the video I showed the times 2, but yeah, I think it does say, are they different? So again, this value here is from a value to the right, so we double it to get our p-value from both tails. So clearly 0.43, I rounded, is greater than 0.01, much greater. So this is when we fail to reject. Okay, so the data that we've collected is not significant enough to say that that null hypothesis isn't true. So what this is saying is that the two pieces of data that we have, the 12 out of 153 and 7 out of 128, are statistically right as we see it right now. There's nothing to indicate that they're totally different. One's maybe by chance, one is not, so it's hard to tell, but we can't reject that null hypothesis that they're roughly the same.